the name, but I won't be talking about blockchain and healthcare systems. I'll be only addressing a small part of artificial intelligence. So what is artificial intelligence? It came into being in the early 40s when computer scientists started thinking that can we make machines intelligent? Can we make machines? Can they think as the humans think? So because we are relating intelligence with human intelligence, so to make machines intelligent, it was decided that let's observe how a human mind thinks, and then we will make how a human brain works, and then maybe we can simulate the same behavior onto a machine. So here comes artificial neural networks. So in the 43s, Warren McCullough and Walter Pitts defined the first artificial cell, which is called a neuron, as the human brains, and is also called a neuron. So onto the screen, you have both the picture of a biological neuron and an artificial neuron. So biological neuron, there is a nucleus, and the nucleus is getting impulses or signals from the cell body of the different organs which are sending it signals that what is to be done. For example, if I touch a hot plate, I immediately, if the temperature is very high, I immediately withdraw my hand because my brain has sent an impulse to the hand that withdraw your finger, otherwise it will burn. So what the brain cell is doing is it is getting impulse or signals from the organs. If the impulse and signals are sufficient enough that it can pass on, it can excite the neuron or the cell, then it will pass the signal to the organs with the help of axon, which terminate into axon terminals. So we want to mimic this neuron cell, biological cell. So what we do is we say that we have to define a cell. So this is a cell or a neuron. What it needs to have is it needs to have input, which can carry input from the various organs or the various blocks when we are talking of the computer system. So we'll be getting, so input in machine learning or artificial intelligence, we have a standard format that input is defined with the help of a symbol which is called X. So input is X. And because it is multidimensional, so we say that input is a vector. So x0, x1, like this, and supposing there are n inputs. So this is the way it is represented. So as you can see here. So every input is connected to the neuron, and we are connecting it, we are weighting the input with whether it is important or not, whether it should have positive importance or whether it should act as a deterrent that we should not do something, so whether the weight is positive or negative. So there is a weight associated corresponding to every input, and that weight we denote with the help of a weight vector which is called W. So for example, I say along with x0 there is w0, along with x1 there is w1, xn there is w1. So what I do is I do a summation of this weight multiplied by its corresponding input, and because the input is not zero centered, so I add a bias term to it also. So I do this summation and I check if this summation is, I apply a function over it because I want the output in a particular range. Supposing I am interested in classification, so I am interested in the output as one is it is a binary classification, so output can be 0 and 1. So if it is 1, I say it is class A. If it is 0, it is class B. So I apply a function over it and squeeze this input, which may be ranging from some positive to some large negative number to large positive number. I want to squeeze it into a small value, which depends on what kind of task I am doing, whether I am classifying the data, whether I am predicting some value, so I am doing some regression or not. And we call this function as the activation function because it will activate the neuron depending on what is the weighted sum of the weights, input and the bias. So this is mimicking how the human brain cell works. So these were loosely inspired by the biology. We are not mimicking biologically how the human brain functions, but we are representing an abstract model of the neuron with the help of some mathematical symbols. So here is the first neuron, which is also called perceptron, which was defined in 57 by Rosenblatt. So you know there is input. Every input is connected to the neuron, which is the cell, with the help of a weight. And what we do, we add a bias into it, and then we apply a function which is checking whether the neuron will fire some signal or not, what kind of output we are getting. And as I said, the input is denoted by the symbol X, output is denoted by the symbol Y, mostly in artificial intelligence, machine learning, etc. So the perceptron is a specific type of artificial neuron, and this is a single layer neuron, and it is a linear model. So for example, my function is, if it is just simply checking the summation of xi wi plus b, if it is greater than some threshold, then I say that the class is A or the class is B. So what it is doing, it is giving me a linear separator. There are two different classes, which are, again, let's say my classes are linear, my data is linearly separable. As you can see on the screen, there are two classes denoted by red and blue. So what this is giving, when I learn through this network, it will give me a linear decision boundary, this function. So that is what we are calling it, that it is a single layer linear model, because what we are doing a linear combination of input and weights, and this will give me this function will give me a linear decision boundary. Is this okay? Is this okay? Anybody can say, because then I'll realize that you are hearing me.
Ma'am, actually, participants cannot unmute themselves. They can put up in chat box. We will convey it here.
Okay. So in the end, so we'll wait in between. We can have that thing that after a particular section is complete, I can talk with the participants, because there are certain things where I need their feedback.
Okay, ma'am. Okay, ma'am. And Ravinder Kirkar is saying okay, ma'am.
Okay. So in my problem, so when these neural networks came, it was advertised massively, and it was said that they have come up with the artificial neurons which are capable of solving any kind of problem. But as we have seen here, because it is a linear combination, we can solve only linear problems. So in the 69, there was a dip in the research of artificial neural networks, because it was identified that they have a limitation. They cannot do non-linear classification. What is a non-linear classification? For example, my classes, again, I have, let's say, two classes, but they are separated non-linearly, as you can see on the screen. So a single separator cannot do the classification. It is class A, and this is class B. So, and what I need is, I need non-linear classification. How do I do that? There was a dip, and later on in the late 70s or 80s, there came the concept of that if we can have multi-layer perceptrons, then we can introduce non-linearity. We can handle the non-linear problems by having the activation function also as. We'll talk about what is activation function, which is again non-linear activation function. So there was introduction of sigmoid activation function here. And when we have multiple layers, remember the perceptron is a single layer network where there is input, there is a neuron, and there is a output. What is multi-layer network? Multi-layer network is like this, where we have an input layer and an output layer, and in between we can have multiple hidden layers. As you can see here, there is a single hidden layer here. This is a hidden layer. Okay, we can have multiple hidden layers. So this network is, every input is connected to every other node in the next layer, and this happens with every layer. Every input node is connected, fully connected to the next layer. So now what I call, now this is a node, this is a node, this is a node. This is the input layer where I am feeding the input. X is the input layer, output layer where I am seeing the output. So these two layers, I am directly interacting with them. I can observe them, but the hidden layers, what they are producing, they are, because they are getting input from a previous layer and feeding the output and to the next layer. So what they are feeding, I am not able to see them directly as a user. That's why they are called hidden layers. So for example, this is one network. So fully connected, and of course, so this becomes my input layer. This is hidden layer. This is output layer. I can have multiple hidden layers, so I can introduce here another layer which may have the same number of nodes. It may have different number of nodes, but every node of the previous layer is connected with every node in the next layer. And let's say this is the output. So this is called a multi-layer perceptron. So when I have multi-layer perceptron, when I have non-linear activations, then activation functions, then I can learn or I can solve any kind of non-linear problem. This is the capability of neural networks, which was identified in the after a dip in the late 60s, when multi-layer perceptron were defined and the feed forward and back propagation algorithm was introduced in the 80s. It brought a breakthrough into artificial neural networks. And here, because there are multiple layers, and the layers, as we keep on increasing the layers, it becomes, the network becomes deep. And that's where the term deep learning is coming from. So what we are doing here, I know that input is known to me, defined by the problem. Output is also defined by the problem. So input and output are defined by the problem. And what I am doing with this, establishing this network, is I have to learn these weights in such a way that for every input, when it is feed into the network, I am producing its correct output, which was given to me at the time of the problem definition. So for example, we are interested in distinguishing objects, let's say tables and chairs. So I feed into the network large amount of images of chair, and with every chair, I am saying that it is class chair. And with image of chair, I am saying it is class chair. With every image of a table, I am saying it is class table. So the data is a supervised learning model where the data has both X and Y. So X is the input and Y is the output. This is who is giving this. This is defined by the problem. In this case, we have images of what? Two class, because we have two classes, tables and chairs. So we have large amount of images of tables and chairs. What we want this network to learn the weights in such a way that for every chair image, my network is giving me output as this is predicting that it is a chair class. And if it is a table class, then it is predicting a table class. So every Y, that my network is producing, let's say that my network, because notations are coming. So what I am doing, I am feeding X into the network, applying a function, and it is producing Y tilde. Y tilde, let's say it is the predicted output. And what was Y? Y was the actual output. So when does my network becomes learned? When my Y predicted is equal to the actual value Y. That is the error, which is, let's say, the difference between Y and Y predicted. And I'll either, because it can be a positive or negative value depending on whether I am doing Y minus Y tilde, Y is large or Y tilde is small. So because there is an error can be both positive and negative. I am only interested in the magnitude of the error, so I can do a absolute value. And because absolute value is non-differentiable, and in machine learning we need a differentiable error function, so usually you'll find the error function as. So what I want is for every sample, this is my error for every ith. Okay, so this is summation I equal to 1 to for n samples, and this should be equal to 0 because 0 is the minimum error. जब मेरे सारे predictions correct होंगे तो मेरा model learn हो जाएगा, because it is predicting for every chair image, it is predicting that it is a chair. For every table image, it is predicting it is a table. Then my network is learned. So that is called training the network. So I'm sure you people know these terms. That's why I'm not going into them deeply. I'm just coming into the nuances of how it is done and what are the various parameters or hyperparameters, the technical terms involved in neural networks. So here I'm showing you one node, what it is doing. This node is from some, okay. Yeah. So here your input are n inputs. And because now I am dealing with multi-layer networks, so every output from a previous layer becomes input to the next layer. So what is the output from the previous layer for any layer? What I am applying an activation function. The notation here is A. The function F is now I am saying that this is A equal to F. So whatever is the output that a layer is producing, this I call as the activated output. So in the 0th layer, which was x0, x1 here, x2, x3, xn, the input goes as it is into the network. That's why there is no weight connected from this input to the activation function. This simply goes straight inside. So we call it activation function at the 0th layer. 0th layer is the input layer. Now this is connected through weights to the next layer. So I have this slide shows you one of the activation function, what it is doing. What it is doing is it is multiplying this input corresponding to this weight. So it is coming here plus W input. Now, what is the notation Wij? The notation Wij is the weight which is connecting the jth node from the previous layer to the ith node in the next layer. So for example here, because I am checking the node in the first layer, which node? The first node, which is a subscript. So A1 superscript is the layer. So I am talking about the first layer. So A1 one activation function में क्या जा रहा है? इसमें जा रहा है आपके पास में W which is coming from connecting the first input to the first output in the first layer. So it is W11 into A10. Then it is connecting the second input from the previous layer to the first input in the first layer. So W12. So कि कौन से नोड को कनेक्ट कर रहे हो, कौन से नोड से, तो कौन से नोड से is J which is coming from the previous layer, and which node in the current layer, so that is I. So I is 1 because I am talking about A1 activation function, and J is varying because there are n J's, it is varying from 1 to n. So you have a summation of Wij, Aij, and which layer, so this layer is subscript. So कौन से इनपुट से को कनेक्ट कर रहा है और कौन से लेयर में कर रहा है, तो ये मेरे पास में आएगा. फॉर एग्जांपल ith में कर रहा है, एंड विच लेयर, यहाँ पे अपन फर्स्ट लेयर में कर रहे हैं. So this is the summation. So is this is okay, I hope you know. And for every term for every activation node there is a bias term also. As I said, this is so that the data is not zero centered. So it is kind of an intercept value if you think of fitting a line into a data. So now it is shown that there is a symbol here which is called a sigmoid activation function. This symbol is for sigmoid. So what this sigmoid is doing, we will see later on. But now you can see that this equation, I have to repeat this for this second node, for this third node, and for all the M nodes in this hidden layer. So now the output that they will produce is M outputs, the output from this first node, second node, and there are M nodes in this hidden layer. So this output is again arranged in a vector. The vector is shown here. How do I get this output? I have now the weight is my weight matrix is my two-dimensional, weight becomes two-dimensional matrix. Every row is giving me weight from the first node in the previous layer to in the hidden layer to the all the nodes from the previous layer. So it is every row is W11, 12, 1n. So all the weights which are connecting all the input nodes to this current node. So the second is the weights which are connecting this second node to the first node. So 2 to 1, 2 to 2, and like this. So you have a matrix which is connecting m output nodes with n input nodes. So this matrix, which is a weight matrix, is nothing but a m by n dimensional matrix. And this is multiplied by how many activation inputs are there. There are n inputs. So it is multiplied by this input, which is A is what? A is n by 1. So what, and then this bias, there are how many nodes in the hidden layer? There are m nodes. So this bias is m by 1. Okay. So when you multiply this weight matrix, which is m by n, with just a moment. So यहाँ पे जो आ रहा है वो क्या आ रहा है, वेट आपके पास में क्या है, m by n, आपके पास में a क्या है, n by 1. So what you will get m by n, and this is added with b, which is also m by n, m by 1, and what you will get as output, you will get m outputs. So you will get a vector which is m by 1. Is this clear? यहाँ पे मुझे ये स्टूडेंट्स को अनम्यूट कर सकते हैं, पार्टिसिपेंट को, ताकि मुझे पता चले ये नोटेशन समझ आ रहा है या किसी को कुछ पूछना है. हेलो.
If anyone is like if anyone says to any response, we can unmute them. Please raise your hand or give anything in chat box. We will unmute them.
Any question, please? So this is okay?
Yes, ma'am. There are no queries as of
Okay,
now.
okay. So this is happening at every activation function, at every node in the network, and you understand it now. So now we are talking of the activation functions. So what are the various activation functions? As I said, the earlier activation function which we were doing is if fx is greater than some threshold, then we say it is class 1A, else class B. So this is a linear classification. So in the 80s, this sigmoid, which is the first non-linear activation function, was introduced. What is sigmoid is expressed as 1 over 1 plus e raised to power minus x. Its value varies from 0 to 1. So when x is a large positive number, then it saturates, its value gives, you get the output as, let's say it is infinity. So e raised to power minus infinity is 0. So what you get is 1. Okay, if x equal to plus infinity. For large negative numbers, when x equal to minus infinity, what you will get is 1 over 1 plus e raised to power minus into minus infinity. So this will be 1 plus infinity. So this is equal to 0. So value of the sigmoid varies from 0 here to 1 here. Okay. And for when the value is 0, then when x equal to 0, so you will get 1 plus e raised to power 0, which is 1 plus 1, which is 1 by 2, which is 0.5. So you can see here how the sigmoid behaves. The sigmoid behaves as a signal S, and it varies from 0 to 1. Similarly, we have another activation function which is called tan h. Tan h, you can see the equation is like this. Only it is also a non-linear activation function. How it differs from the sigmoid is its value. Sometimes we want to do classification as -1 and 1 instead of 0 and 1. So tan h is the appropriate function for that, because its output varies from large negative value, and the input is a large negative value, it converges to -1. And when the input is a large positive value, it converges to +1. So values are varying from -1 to +1. Now later on, because the sigmoid leads to vanishing gradient problem, so which actually then which leads to convergence problem in the learning of the network. So there came up the ReLU activation function. What is a ReLU activation function? It clips all the negative values to 0, and it outputs the same value x as output when it is a positive value. So for positive values, the output is equal to input, and when you will take a gradient of this value, that is the derivative of this value, the derivative is 1. So there is no vanishing gradient problem. And why a vanishing gradient problem comes in sigmoid is, you can see in the diagram here that for large positive values, the sigmoid will saturate to 1. So when I am taking a differentiation here with a small change in x, what is a change in y? The change in y is almost 0. So that's what it is saying, that when the derivative of the sigmoid comes as 0. And similarly, it comes as 0 or near about 0 when it saturates to large negative values. And as the networks learn, this saturation happens very fast, which leads to the vanishing gradient problem. Gradients are required when we are doing gradient descent in learning the network. We will minimize the error by following gradient descent algorithm. And if we have these are capable of handling binary classification. If we have multi-class classification, where let's say the class output is varying from 1 to n number of classes, then there is a softmax activation function. What does this softmax activation function does? The output is every node output at the output is doing what? E raised to power xi over summation of e raised to power xi, where I is varying from I is varying from 1 to the number of classes. So e raised to power xi is kind of producing some values at the output. For example, the values are 1.5, 2.4, 6.7, 8.5. And this is e raised to power x. E raised to power. This is how softmax behaves. This is kind of e raised to power xi. And when I am softmax will do what? It will divide this every value with the sum of these values. 1.5 plus 2.4 plus 6.7 plus 8.4, so that you get a probability value for every value, and whichever class has the highest probability, normalize कर रहे हैं आप इसको, you will do that is the most probable class. So एक बार इसको cleanly लिख देती हूँ, just you have idea. So for example, EXI, EXJ is equal to 5, 2.4, 0.5, 6.5. So this value here will be equal to 1.5 divided by 1.5 plus 2.4 plus 0.5 plus 6.5. You will get a normalized value, and every value is divided by that. So you will get this is the summation. I hope it is clear. Otherwise, you can always send a message. So now why we need multiple layers, why we are, and how many layers are appropriate? As we can see that any two-layer network, this is the universal approximation theorem, says that any two-layer network can learn any non-linear problem. However, the learning is good when we increase the number of layers in the network. So what each layer is doing, and and how many layers should we have in the network? This is conceptually what is happening is something like this. So for example, you have images of certain shapes, and you are interested in identifying whether it is a box, whether it is a vertical shape, horizontal line, or it is a diagonal line. For example, your input is a 2 by 2 image. So 2 by 2 image is something like this. ऐसा image. So इनपुट आपके पास में देख रहे हैं, ये अपनी इनपुट लेयर है. तो इनपुट लेयर में मेरे पास में क्या है, आप यहाँ देख रहे हो कि इनपुट इज अ वेक्टर, एज आई टोल्ड यू. सो हाउ डज दिस वेक्टर इज फॉर्म? दिस वेक्टर इज फॉर्म बाय फ्लैटनिंग दिस इनपुट. सो ये मेरे पास में ऐसे बनती है. सो दिस पिक्सल कम्स हियर, दिस कम्स हियर, then let's say this pixel and this pixel. So that's why it was 2 by 2 was the original image. When I flatten it in the vector form, I get a 4 by 1 vector. So अगर मेरे पास में ऐसा इमेज है जो आपको स्क्रीन पे दिख रहा है, तो उसमें आपके upper 2 pixel, and now what is that every pixel is a value which is if it is black, that means it is -1. It is white, that means the value is +1. And if it is gray, that means the value is 0. So let's say मेरे पास में ये 3 different shades मैं दिखा सकती हूँ इस input के अंदर. So if it is the pixel is 0, that means the value of the pixel is varying from -1 to +1. ओके, एक्स का वैल्यू ऐसे वेरी कर रहा है. एंड फॉर एग्जाम्पल, सो जो फर्स्ट लेयर है जो आपको स्क्रीन पे दिख रही है, व्हाट इज द फर्स्ट लेयर? दिस ब्लू दैट आई एम मार्किंग इज द फर्स्ट लेयर. सो आप देखेंगे कि फर्स्ट लेयर में एवरी न्यूरॉन इज कनेक्टेड विद द सिंगल पिक्सल वैल्यू. सो दिस इज लेट्स से x0, x1, x2 and x3. सो आउट ऑफ द 4 पिक्सल्स इस न्यूरॉन की वैल्यू किससे इफेक्ट हो रही है? इसकी इफेक्ट हो रही है कि ये टॉप पिक्सल क्या है जो ब्लू है, ओके। एंड ये टॉप पिक्सल, ये न्यूरॉन कब फायर करेगा? जब टॉप पिक्सल की वैल्यू 1 होगी, बिकॉज 1 इज द हाईएस्ट वैल्यू, +1 is the highest value. And rest of the values, so I'll keep this as white, let's say, which is the highest value, and the rest of the values are don't care for it. Okay, so don't care is kind of, मैं इसको कर देती हूँ कि it doesn't matter. इसको doesn't matter को let's say yellow से लेते हैं अपन. So it doesn't matter what are the values here. But if this value is 1, then this neuron is active. It has the highest value, that is, it is switched on. Similarly, for the next pixel, it will be switched on when this is white and the yellow portion is don't care. The third pixel will be switched on when this pixel is 1 and the rest of the pixel are don't care, and the last pixel will be switched, the neuron will be switched on or it will be excited when this pixel is 1. If it is +1, इसका value +1 है, इसका +1 है, इसका +1 है, इसका +1. So this is called a receptive field of a neuron. So receptive field of this neuron, the first neuron, is what? Only this pixel. The receptive field of the second neuron is only this pixel, which is the second pixel. Only this pixel. Yeah, this pixel. And the receptive field of the third neuron is this. What is affecting the value of this neuron? अभी ब्लैक मत देखिए आप, आपको केवल ये देखना है कि मैं बता रही हूँ कि एक न्यूरॉन कब फायर होगा, जब इसके जो 4 पिक्सल में से केवल जो व्हाइट पिक्सल है वो +1 है एंड रेस्ट ऑफ द पिक्सल की कोई भी वैल्यू है, इट डजंट मैटर, इट डजंट मेक एनी डिफरेंस. सो व्हाट डजंट मेक एनी डिफरेंस, उसको मैं येलो से दिखा रही हूँ. आई होप इट इज क्लियर. नाउ coming to the second layer, this was the input layer, this is the first layer. So let me mark the first layer with blue, first layer. Now in the first layer, you see that, and the arrows are connecting every node in the network to every other node in the next layer. And if it is denoted as black arrow, then the weight is, this is the weight. So weight is varying from +1 to -1. अभी हमने यही किया है, और 0 भी हो सकता है. So 0 is when there is no connection. कहीं बीच में connection भी नहीं है, तो that means there is a 0 weight. That's why हमने वो connection हटा दिया है. And जहाँ +1 है, the connection is, the weight is a black arrow, and where the weight is a negative, then it is a red arrow. So when I am connecting for this network, for this node to fire, because this node is connected to this first node from the previous layer and the fourth node from the previous layer, तो इसका receptive field क्या हो गया? ये 2 पिक्सल अगर 1 होंगे तब ये node will fire, and these are the don't care. These doesn't matter कि इन पिक्सल की वैल्यू क्या है. Similarly, the second node will fire, it is connected with the second neuron and the third neuron. So ये दोनों आपके पास में second और third इसका जब 1 होंगे तो ये फायर करेगा, और जब ये कुछ, चाहे ये 2 कुछ भी हों. Similarly, for this third neuron to fire, its receptive field will become, it is connected with the first neuron, so this is the first, and it is connected with the last. So इनकी वैल्यूज क्या हैं? ये दोनों 1 होंगी तो ये फायर होगा, तो ये आपके पास में कनेक्शन ऐसा है, तो ये डोंट केयर हो जाएगा. एंड सिमिलरली यहाँ पे जो लास्ट न्यूरॉन है, इस लास्ट न्यूरॉन में वैल्यूज कहाँ से आ रही है? सेकेंड न्यूरॉन से आ रही है, और इसमें किससे? थर्ड से आ रही है. तो ये दोनों की वैल्यू क्या होगी, उसके बेसिस पे ये फायर होगा, और ये डोंट केयर है. So don't care is marked with the color, and the white pixels which are required are marked by the boundary. So you see that as I am increasing the layer, the receptive field of the neuron is increasing. Here in the 0th layer, which is the input layer, 0 layer, here the neuron is affected by a single pixel. In the first layer, a neuron is affected by 2 pixels. And similarly, in the second layer, the neuron will be affected by here. For example, you can see at the top, you can see that it is affected by this, so which is this pixel and this pixel, and this is affected by the second also, which is this pixel as well as this pixel. So it is affected by all the 4 pixels. So as the depth of the network increases, the receptive field becomes complex because it is now affected by more number of pixels. It is affected by more number of inputs. So the number of inputs which are affecting the neuron is increasing. So the complexity of the network start increasing as the depth of the network is increasing. So you can see here कि अगर मैंने first 0th input पे अगर कोई एक point भी मेरे पास होगा तो ये न्यूरॉन फायर हो जाएगा. फर्स्ट लेयर पे आप देख रहे हो कि एक वर्टिकल लाइन आएगी तो ये टॉप न्यूरॉन फायर होगा. सेकेंड न्यूरॉन पे ये कब फायर होगा? जब ये चारों पिक्सल 1 होंगे, यानी एक सॉलिड आउटपुट आएगा विच इज अ बॉक्स. सो आइदर इसकी 1 वेट होगा तो ये व्हाइट बॉक्स है, और अगर ये सारी नेगेटिव वेट हैं तो ये ब्लैक बॉक्स है. सो ये दोनों केस में यहाँ पे मेरे पास में आउटपुट मुझे ये बताएगा बॉक्स. सो जब मेरे पास में अर्ली लेयर्स हैं, व्हाट आर दे लर्निंग? They are learning the basic primitives, and as the number of layers increases, the information that they are learning is getting complex. तो पहले हमने point learn करा, पॉइंट्स को मिला के फर्स्ट लेयर ने लाइंस लर्न करे, सेकेंड लेयर्स ने लाइन को मिला के कॉर्नर्स लर्न करे, नेक्स्ट लेयर ने उन कॉर्नर्स को मिला के शेप्स लर्न करा. सो अर्ली लेयर्स आर लर्निंग लो लेवल फीचर्स which are, you can say, points. Middle layers are, you can say, lines. Then lines ko join karke intersections. And then finally we have shapes. So as the depth of the network increases, we are going towards, early layers are low level features and later layers are learning high level features, which in this case is shapes. एंड यहाँ पे जो डायग्राम है आपको, वो डायग्राम आपको क्या बता रहा है? वो आपको एक सैंपल इमेज दिया है विच इज अ हॉरिजॉन्टल लाइन, एंड जब आप इस नेटवर्क से इसको पास ऑन करोगे तो आप देखोगे कि ये इसमें केवल ये, और जो ये न्यूरॉन में जो आपको यहाँ पे दिख रहा है ग्रे कब होगा? जब उसका इनपुट आपके पास में, फॉर एग्जाम्पल मैं फर्स्ट का बता देती हूँ. दिस इज अ पॉजिटिव वेट, द इनपुट वाज -1. सो यहाँ पे -1 गया, -1 गया तो ये न्यूरॉन इज अ नेगेटिव न्यूरॉन, तो ये ब्लैक हो गया. जब आपके पास में नेगेटिव वैल्यू होगी तो ब्लैक हो रहा है. फिर आपके तो ये अब इनपुट जाएगा नेक्स्ट न्यूरॉन में विच इज अ पॉजिटिव वेट, बट द इनपुट इज नेगेटिव, तो एक नेगेटिव इनपुट जा रहा है. यहाँ पे जो नेक्स्ट आपके पास में है वो भी आपके पास में इसका वेट आपके पास में लास्ट न्यूरॉन है विच इज अ +1 वैल्यू. सो ये व्हाइट है क्योंकि ये फायर हुआ है, और ये भी वेट इसका +1 है. तो +1 एंड -1 विल बी 0. तो आपके पास में इसके अंदर जो 0 जा रहा है तो इस नेटवर्क को ग्रे कलर दिया हुआ. तो जहां पे वैल्यू -1 जा रही है वहां पे वो ब्लैक न्यूरॉन दिखाया हुआ है आपको, जहाँ पे वो +1 जा रही है वहां पे वो फायर करता है और व्हाइट न्यूरॉन दिखाया है, और जहाँ पे वो 0 वैल्यूज हैं वहां पे वो ग्रे हैं. तो इस इनपुट शेप के लिए जब आप उसे रन करेंगे तो ओनली दिस न्यूरॉन विल फायर बिकॉज इट इज एग्जैक्टली द shape which is coming from the input, and this will be classified as a horizontal line. So do you want me to run this example, or you will be able to run? Because the concept I have shown you that how it is learning. So any response from the participants?
Participants can mention their response in chat box. We will unmute them or convey the message.
Clear. Okay, perfect. Thank you. So now you learn, you see that what are the layers doing? The layers are breaking the problem into small problems. So for example, you have to do handwritten digit recognition. So you have 4 examples of digit images here, that it is a 1. So it is a combination of straight line. So if it is this, one layer learns this, another node learns this, another node learns this, and when they are all connected through, it will be able to classify it as a 1. If it is a 0, then it consists of small lines which are this. If all are there, then we can classify it as 0. If it is a 9, it is a combination of 0 and a straight line, that is a loop and a line. If it is a 8, it is a combination of 2 loops. So earlier layers we learned these lines and the loops as small segments of lines. The hidden layers will combine these and lead to the formation of a shape as we proceed towards the output layer. So layers break the problem into pieces, and you can see that now this is a image of a 9, and this 9 can be, you can say that it consists of a grid of pixels. ये 28 by 28 के पिक्सल हैं. So input हमारा क्या हो जाता है? Input is 28 by 28, which is equal to 784 input. और ये 784 क्या है? Every row of the image is flattened and becomes a vector. In next vector, these are appended together and you create the input vector, flattened. Okay, and इसमें जहां जहां white है वो आप देख रहे हो, ये network, let's say ये nodes white. So ये जो connected है इनमें से these will fire some nodes here, which will then combine and fire some nodes here while we are learning. And we know that it is a 9. So ultimately this should fire. So this is how it will learn. So that's why we add number of hidden layers, because we want to subdivide the problem. It is divide and conquer, divide into small problems, and the intermediate layers are adding something into the previous layer and coming to a conclusion as we proceed towards the output layer. So what is done here, neural network में होता क्या है? It is, let me come to the algorithm that I quoted, that in 80s Rumelhart came up with the feed forward and back propagation algorithm for neural networks. What it does is, let's say we have a network of 3 nodes in the input layer, 2 nodes in the output layer, hidden layer, and this is one output layer. So if input is X, connected through a weight which is coming from this node to which node is denoted as ij. So the activation function F1 as shown on the screen is what? It is Wx from first to first into x1 plus W from the second node to this first node into x2. And I apply a activation function which will give me an output, and let me call it as, because I am calling it output of this node, so I can say it is y1. So similarly, y2, which is produced as output from the second node, is what? It is, you can see here, it is W, which is connecting x1 to the second node. So W x12 into x1 plus W x2 connecting to 2 and x2. And I apply activation function F2. Usually in a layer, all the activation functions are same. Usually in a network, all the activation functions are same except for the last layer, which may have, if it is a multi-class problem, it may have a softmax function. Otherwise, it can have, if it is a classification problem, binary classification, it can have a sigmoid activation function. And the hidden layers, usually nowadays, they are ReLU as a activation is preferred because it takes care of the vanishing gradient problem. So similarly, you will get an output at the third node, which is like this, summation of the weights and the corresponding input, you get F3. Now, once you get Y1, Y2, and Y3, this becomes an input for the next layer, which is another hidden layer, F4. There are two nodes in it, F4 and F5. So F4 will be Y1 into W1 to 4. So this is F4. So this is the weight which is connecting the first node from the previous layer to the fourth node in the current layer. So that's why it is called W14 into Y1 plus W24 into Y2 plus W34 into Y3. This will give me Y4. Similarly, I'll compute Y5, which is W15 into Y1, W25 into Y2, W35 into Y3. Now to get output from F6, it will be W weight, which is connecting the fourth node to the sixth node into Y4, plus weight, which is connecting the fifth layer node to the sixth node, and you get a final output, which is Y. Okay, so to the viewer, this step, which is we are feeding the input from the input layer, passing it through the activation functions in the intermediate layers, and getting an output at the output layer is called feed forward, because we are feeding the input forward. Okay, so we do a feed forward for one input, we calculate output, we do a feed forward for another input, we do a feed forward for another input, and this we do for all the inputs. How many inputs do we have? We have m inputs. What is the dimension of the inputs? It is, let's say, m dimensional. So यहीं पे मैं आपको कुछ मैथमेटिकल नोटेशन बताना चाहती हूँ, क्योंकि वो हमारे पास में आपको समझ आना चाहिए कि ये कर क्या रहा है. Let's say, so let's say we are solving the digit, handwritten digit. So I said it is a image, input is x is what? X is 28 by 28. So when I flatten it, x becomes, it is 784 by 1. All right. So अगर मैं नेटवर्क बनाऊंगी तो मेरे पास में लेट्स से ये इनपुट है, ये कितनी है 784, ये एक इनपुट है. ओके, एंड लेट्स से मैंने हिडन लेयर लिया 1, एंड देन आई हैव आउटपुट. एक छोटा एग्जांपल ले रहे हैं, एंड इस हिडन लेयर में लेट्स से मैंने 10 नोड्स लिए, एंड आउटपुट, बिकॉज मेरे पास 10 डिजिट्स हैं, इट इज अ मल्टी क्लास classification problem, so this also has output has 10 nodes. So मेरे पास में फर्स्ट जो लेयर है उसमें से अपन अगर बोलेंगे तो the notation that we are using is कि a 0th layer. तो लेयर हम किससे डिनोट करते हैं? सुपरस्क्रिप्ट से. तो a0 क्या है मेरे पास में 784 एक इनपुट है, और मेरे पास में कितने इनपुट हैं? लेट्स से मेरे पास में m इनपुट हैं, तो इट विल बी 784 बाई m. ओके, अब मेरे पास में जो हिडन लेयर है, जो फर्स्ट हिडन लेयर है, वो जो आउटपुट दे रहा है, लेट्स से ये मैं समेशन ऑफ wij, xi को मैं क्या बोल रही हूँ, लेट्स से आई कॉल इट एज zj, zi, ओके, समेशन को। तो ये मेरे पास में जो हिडन लेयर है वो क्या कर रही है, इनपुट जो मेरे पास में है वो ये z, लेट्स से फर्स्ट नोड को अपन बोल रहे हैं z1, सो ये z1 जो समेशन है उसको, तो z1 मेरे पास फर्स्ट लेयर में है, तो सुपरस्क्रिप्ट 1 हो गया। वो क्या है, ये वेट मैट्रिक्स जो इसके ऊपर आ रही है, और ये क्या है, एक्टिवेशन फंक्शन जो 0th लेयर का है, प्लस जो फर्स्ट लेयर में बायस है, ये z1। इज दिस ओके? तो ये क्या होगा, अभी वेट मैट्रिक्स मुझे क्या होंगी, अब आप देखिए यहाँ जो वेट मैट्रिक्स आएगी W, ये जो W1 आएगी, ये W1 क्या होगी, ये 784 प्रीवियस नोड्स को 10 नेक्स्ट नोड्स को आ रहे हैं। तो ये मेरी जो W1 है वो है मेरे पास में कितने आउटपुट हैं, 10 है, और इनपुट कितने हैं, 784। बिकॉज हम कैसे इसको मार्क करते हैं, कितने नोड्स पे कनेक्ट हो रही है और कितने नोड्स उसके इनपुट हैं। आई होप इट इज ऑल राइट, ओके। एंड एक्टिवेशन आपको पता है मेरे पास में कितने थे, 784 बाई कितने, जो m है, जो 0th लेयर कितने आउटपुट निकालेगी, 7 m मेरे पास में डिजिट्स हैं जो जिनसे मैं ट्रेन कर रही हूँ, एवरी डिजिट इज 784 का वेक्टर। सो मेरे पास में एक मैट्रिक्स हो जाएगी, वो मैट्रिक्स क्या होगी, 784 बाई m। अब जब मैं इसको मल्टीप्लाई करूंगी तो आप देखिए, डू वी कंफर्म द इनर डायमेंशंस, तो z है, वो z मेरे पास में आउटपुट क्या आएगा, w मेरे पास में क्या है, w मेरे पास में 10/784, a मेरे पास में क्या है, ये है मेरे पास 784/m। तो इन मैट्रिक्स को मल्टीप्लाई करेंगे तो आपके पास में क्या आएगी, आपके पास आएगी 10/m, और बायस टर्म्स आपके पास में कितनी है, 10 है, और ये कितने हैं, 10 तो इनका डायमेंशन है कि, और कितने हैं, m, जितने m वैल्यूज हैं उन सब के लिए आपके पास में बायस टर्म्स हैं। तो यहाँ पे आपके पास में ऐड हो रही है ये 10/1 प्लस 10/1। तो आउटपुट आपके पास में z क्या आएगा, तो z आपके पास में आएगा 10/m। आई होप दिस इज ओके। एंड सिमिलरली मैं इस आउटपुट को क्या बोलूंगी, जो नेक्स्ट हिडन लेयर है, इट इज अ सेकेंड लेयर, सो आई विल कॉल इट एज A2, दिस आई एम कॉलिंग एज A1, दिस आई एम कॉलिंग एज A0। ठीक है, तो मैं यहीं पे आपको इसी नोटेशन को फॉलो करते हुए Z2 भी बता देती हूँ कि क्या होगा, यहाँ से जो आउटपुट मिलेगी वो मिलेगी Z2, ये Z1 है, 1 सुपरस्क्रिप्ट लिखना है, ओके। तो Z2 लिखूंगी, यार थोड़ा हौच पौच हो रहा है, बट आई होप कि आपको समझ आ रहा हो, कोई आप लोग बता भी नहीं रहे मुझे। Z2 क्या हो जाएगा, Z2 विल बी W2 into A1 plus B2, ओके। सो आई नो कि W2 मेरे पास में क्या है, 10 आर कनेक्टेड टू 10, तो ये है 10/10, ये मल्टीप्लाई हो रहा है। A1 कितने हैं मेरे पास में, A1 मेरे पास में 10/m है, अभी अपन ने निकाला है ना ये। A1 is what, A1 is f of Z1, तो जो Z1 है वो ही रहेगा। तो मेरे पास में ये हो गया 10/m, और B2 भी मेरे पास में क्या है, 10/m, so Z2 is also 10/m। एंड सिमिलरली यू कैन सी कि Z2 पे जो सॉफ्ट मैक्स आगे आपके पास में ये सॉफ्ट मैक्स फंक्शन लगाएंगे, वो आपके पास में कितनी आउटपुट आएंगी, 10 आउटपुट्स आएंगी, कितनी आएंगी, ये 10 बाई m सैंपल्स हैं तो m सैंपल्स की आउटपुट आएंगी। सो यू नो दैट आप देखिए इस नेटवर्क को अगर मुझे लर्न करना है तो मेरे पास में पैरामीटर्स कितने हैं। फर्स्ट 0th layer and first layer को we are connecting with the weight matrix, which is how many weights I have to learn, 780 by m. This, and then I add it the biases also, which is 10 by m. Then the next layer is 10 by 10, 10 by m, and then so it is kind of 780 by 10 plus 10 by 780 by m plus 10 by m. These many number of weights I have to learn. So as the number of layers in the network increases, the number of parameters, what are parameters? The values that we are learning in the network are called parameters. Here that is the weights that I am learning, the weights and the biases. And how many layers I have to find, how many nodes I have to keep in those layers, what are the activations functions that I am deciding. These are the design hyperparameters which the user decides कि मुझे कौन से एक्टिवेशन फंक्शन किस लेयर में लगाने हैं, कितनी नंबर ऑफ लेयर्स लगानी है, कितने नंबर ऑफ नोड्स हर लेयर पे लगाने हैं, बिकॉज ये आप ह्यूरिस्टिकली डिसाइड कर रहे हो, ये हम लर्न नहीं कर रहे. दैट्स व्हाई दे आर कॉल्ड हाइपर पैरामीटर्स. द पैरामीटर्स इज व्हाट वी आर लर्निंग, विच इज द weights in the network. What is defined by the problem, the input and the output is defined by the problem. So we have till now we have learned a feed forward step where every input is passed through a network, it produces an output, that output will be compared with the output given in the training data along with this input कि इस हमारे पास में training data क्या है, x is the training data, इसके corresponding हमारे पास में output दिया हुआ है which is y. तो every x becomes a row, x1 x2 and ये मेरे पास में कितने हैं, m थे, इतना x, तो मेरे पास y भी कितने, तो ये मेरे पास में x हैं, m है, और हर में लेट्स से n पिक्सल्स हैं, m by n. y कितने हैं मेरे पास में, m by 1, क्योंकि हर इनपुट के कॉरेस्पॉन्डिंग मेरे पास में एक y है, y1 y2 and yn. दिस इज द ट्रेनिंग डेटा. सो मेरा हो क्या रहा है, एक्स मैट्रिक्स मल्टीप्लाई हो रही है, किसके साथ में मल्टीप्लाई हो रही है, वेट मैट्रिक्स प्लस बायस ऐड हो रहा है, और वो क्या प्रोड्यूस कर रहा है, वाई कैप. दिस वाई कैप आई हैव टू कंपेयर विद द, क्योंकि यहाँ फंक्शन लग रहा है एक्टिवेशन फंक्शन, विद वाई एंड आई हैव टू डिसाइड द एरर. सो एरर क्या होगा आपके पास में, error is the difference between what you have produced and what was the actual value. Let's say the actual value is z in this diagram and the output produced is y. So what is the error? The error is denoted as del, which is z minus y. और error आपके पास में कहाँ produce होगा, at the last layer of the network. The hidden layers are producing some output which becomes input for the next layer. So we are not we cannot see those the hidden layer, what is the error produced by the hidden layers is not known to us. So how now this error, what node is causing what effect on this error, that we have to now find out. So we have to check that if I do a slide, remember what we are learning, we are learning the weights. So I have to decide what effect will come onto this error if I slightly change the weight between this node and this node. So I have to now, the algorithm that we follow in learning the network is, we are interested in minimizing this error. How do we minimize? We form the error as a convex function, which is like a ball. So that's why I said we will do z minus y quadratic function लेंगे. This is the del. So इसमें ये क्या कह रहा है आपको? ये कह रहा है कि ये error, let's say this is the error, this is error, and this is the weight. So it says that if I increase the weight by a small amount, what error does it produce? So I am interested in obtaining the minimum error. The minimum error is somewhere here. So if I am somewhere here, then what I want to do, I want to go in the gradient of, the slope is gradient of E with respect to weight here. So the slope is increasing here because जब मैंने weight को increase करा तो यहाँ error increase हो रहा है, तो मुझे error को decrease करना है, तो मुझे किस direction में जाना है? मुझे इसके negative direction में जाना है, weight को decrease करना है ताकि मैं minimum error पे आऊं. And if I am on to this side of the error surface, तो यहाँ पे मेरे पास में gradient क्या आ रहा है? आ रहा है कि when I am doing a slight increase in weight, then the error is decreasing. ये increase करा तो यहाँ पे error बड़ा था और ये decrease हो रहा है. तो मुझे zero पे आने के लिए इसमें क्या negative आ रहा है, तो मुझे यहाँ पे because the slope is negative, I have to add something it to arrive at the zero error. So this is called gradient descent. So wherever you are, you do proceed in the negative direction of the gradient of the error with respect to weight, so that we come at the minimum error position. Okay, this we do iteratively. Okay, so that is called minimizing the error using gradient descent. So we will apply this algorithm of gradient descent with the back propagation of error. So what is this back propagation of error? I'll show you here. Conceptually what it happens is कि ये एरर जो आ रहा है इसमें इस नोड का कंट्रीब्यूशन क्या है? इस नोड का कंट्रीब्यूशन, दिस नोड, फोर्थ नोड इज कनेक्टेड टू द सिक्स्थ नोड via a weight which is W46. So it says that the error that this node F4 is producing is kind of proportional to the weight which is connecting it to the next node and the error which is produced at the next node. So this is W46 into error. So and the weight, the error which is F5 is causing is proportional to the weight which is connecting F5 with F6, which is W56 into the error which is produced at the last layer. So this way we keep on going back. So we back propagate the error from the output layer to the input layer. This is back propagation. So how each node is affecting the error? So it is affecting in proportion to its corresponding weight, via which it is connected to the node from a previous layer to the next layer. So we back propagate the error from the last layer till the first layer, and then we update the weights. So how do we update the weights? We update the weights. So here in this diagram, you can see the error which is contributed by node F1 is the error, it is a summation of error contributed by node 4 into its corresponding weight, which is W14, plus the error which is contributed by F5 into W15, which is shown here. So that way I'll compute all the dels, del 2, del 3, and del. And now I have to update the weights. So how do you update the weight? You update the weight by following gradient descent, which is W plus plus equal to the previous weight minus a learning rate into del, which is partial differentiation of error with respect to the weight, the corresponding weight. For example, this is I. So I. Okay. So in this diagram, what the error was, I think z minus, let me see, z minus y. So when we differentiate, error equal to z minus y ka whole square. So when I differentiate error with respect to weight, z is what? Z is w matrix into x जो था आपके पास में. तो जब आप इसे डिफरेंशिएट करेंगे एरर को विद रिस्पेक्ट टू वेट, तो कॉरस्पॉन्डिंग x आ जाएगा. तो वो यहाँ पे इस केस में जब अपन अगर सपोजिंग यहाँ पे मैं आई एम डिफरेंशिएटिंग इट, y प्रोड्यूस किया था, या y इज द प्रिडिक्टेड एंड z इज द एक्चुअल जो हमने इसको दिया था. तो जब इसको अगर अपन डिफरेंशिएट करेंगे एरर को विद रिस्पेक्ट टू what change in y brings what change in error, so this becomes 2z minus y into I differentiate y with respect to itself, so it becomes minus 1. So ये आपके पास में जो यहाँ पे वेट अपडेट रूल है, ये वो आपने क्योंकि ये कर रखा है z माइनस वाई, इसलिए डिफरेंशिएशन में माइनस 1 आता है, तो ये इसको प्लस कर दे रहा है, इसलिए यहाँ पे प्लस आया है. हैड इट बीन y माइनस z तो ये माइनस ही आता, तो इसलिए उसका वो यहाँ पे माइनस साइन होता. तो ग्रेडियंट डिसेंट रूल इज एक्चुअली दिस विच आई एम राइटिंग हियर, द प्रीवियस वेट minus the learning rate into differentiation of the error with respect to the weight which we are trying to update, and we'll check how we compute this differentiation. Is this okay? This is standard gradient descent algorithm. You increase or decrease the weight by moving a small step in the negative direction of the gradient of the error with respect to the weight. It is coming, this name is coming from the hill descent algorithm, which is if you are at the top of the hill and you want to go at the bottom where the error is minimum, at a time you take a small step in the negative direction of the hill. So that is the gradient descent, because you have to move in the descent. And why a small step? Because if you will take a big step, aap jump karoge to you will fall down the valley, and then you may roll down onto the other side of the hill. There is another ascent. So you will never go stationary at the bottom of the hill. You will be going from one side to the other side, which is called skipping over. So आपको ग्रेडियंट डिसेंड करना है तो बहुत बड़ी स्टेप नहीं करनी, वरना आप यहीं उछलते रहोगे. So what you do is a small step at a time so that you come at the bottom. So this learning rate is very stop. And in small step in which direction? In the negative direction of the gradient. यहाँ पे gradient is positive, यहाँ पे gradient is negative. So where it is positive, you decrease something. Where it is negative, you add something so that you are at the bottom or the minimum. This is gradient descent algorithm. तो ये हम यहाँ पे follow करके weight update करते हैं. When the weight is updated, you feed forward the input again, you compute the output, you compute the error, you back propagate the error to the all the nodes, and then you update the weight, and then you again feed forward all the inputs. So the inputs are feed forwarded all at once. जो अपन ने वहां पीछे देखा था, all 784 by m, which will produce the output, which is 10 outputs for all those m inputs, and we compute the error and we back propagate the error back. This is called feed forward back propagation algorithm. So I come back to the previous जहाँ पे अपन थे, तो हम learning किससे कर रहे हैं? We do the learning by feed forward back propagation algorithm. How the back propagation of errors is happening, we'll understand the partial differentiation with the help of an example here. So for example, you have 4 nodes which are connected to each other in this sequence as shown on the screen. And here this is A0, this is A1, this is A2, and this is A3. So as it is shown here, activation function at the lth layer is a let's say every activation function is a sigmoid function. So this is a sigmoid function. What it is doing, it is multiplying. So for example, A1. ये A1 क्या है? A1 is sigmoid of W1, which is connecting A0 to A1 into A0, which is the previous input, plus B1. Okay. So AL is sigmoid of WL, which is connecting L-1 layer to the Lth layer, and the activation function produced at the L-1 layer plus B1. So यहाँ पे अपने पास में A1 equal to kind of A0 into W1 plus B1. What is A2? A2 is A1 into W2 plus B2. What is A3? A3 is A2 into W3 plus B3. Okay. So the last activation is the Lth layer. So AL is sigmoid of WL plus AL minus 1 plus BL. So how it is getting connected? Every activation function will, last layer is multiplying WL into AL minus 1 and adding BL to it. So this summation WL AL minus 1 plus BL, we call it as ZL1, and when we apply a activation function over it, we call it the activated output, which is AL, and it is producing C0 as output. Now my error is given a Y. The error is C0 minus Y whole square, or it is Y minus C0 whole square. So this is kind of this. So if I extend up to the previous layers, so I get, here I had ZL. Similarly, I'll have a ZL minus 1. So what is ZL minus 1 connecting? It is equal to WL minus 1 into AL minus 2 plus BL minus 1. इसी equation का. So ZL minus 1 is nothing but sigmoid of WL minus 1, AL minus 2 plus BL minus 1. And this can go to the previous layer also. ZL minus 2 क्या हो जाएगा? Sigmoid of WL minus 2, AL minus 3 plus BL minus 2. So ऐसे ये हमारे पास में, because it is a deep neural network, we have number of hidden layers. How many hidden layers? There are L hidden layers. What is the output layer? The Lth layer. What is the input layer? The 0th layer. In between layers are varying from 0 to L minus 1. So now, how sensitive is the cost, the output that I am producing, to small changes in weight? That is what I said in gradient descent. We want to find out what small change in weight is bringing what change of loss in my network. So you know that I am expanding this here, this block. Now this block is shown here. So what are the three variables which are affecting cost C0? It is affected by AL. And what is AL dependent on? AL is dependent on ZL. And what is ZL depending on? ZL is a multiplication of WL into AL minus 1 and plus BL. So in order to compute the change in the cost with respect to, let's say I am interested in WL, but I know that cost is a function of only AL. यहाँ पे ये कॉस्ट है, ये किसका फंक्शन है? ये तो AL का फंक्शन है. So I can differentiate cost only with respect to AL, and the AL is a function of ZL. So I'll differentiate AL with respect to ZL, and ZL is a function of weight. So this will give me the effect of change in weight over the cost. This we get by applying chain rule of differentiation. Is this clear? What this diagram is showing is what is the effect of, if I do a small change in weight, how does it affect the cost? So small change in weight will bring a small change in Z, which will bring a change in A, which will bring a change in C. This is chain rule. Okay, so which is shown here. Partial differentiation of cost with respect to the weight is, cost is a function of Z. So it is, this cost is a function of, AL. So I differentiate cost with respect to AL. AL is a function of ZL. So I differentiate multiply it with the differentiation of AL with respect to ZL. ZL is a function of W and AL minus 1. So there I differentiate it with respect to WL minus. So it is a product of these three terms on which cost is depending. It is depending on AL, differentiated partially with respect to AL. It is dependent on ZL, differentiated partially with respect to ZL, and which is dependent on ZL. This is how you get how much a small change to AL brings a small change to cost, is what the last term is telling you. This term, how much a change in ZL brings a change in AL, is what this term is telling you. And what the first term is changing, how a small change in WL is bringing how much amount of change in ZL. I hope this chain rule is clear to you. Participants, is it clear? Anybody? Is this clear? So the constituent derivatives are shown here because ZL is WL plus AL minus 1 plus BL. So if you differentiate ZL with respect to WL, what you will get? You will get AL minus 1. The AL is a sigmoid of ZL. So differentiating AL with respect to ZL will be derivative of the sigmoid function. Then you have cost. Cost function is your, what are the actual values? Cost is AL minus Y ka whole square. Differentiating cost with respect to AL is 2 into AL minus Y. So the three terms, what every term is contributing is, this is this term, this is this term, and this is this term. So this is how the error at the last layer is varying with respect to weight which is connecting the previous layer to this layer. ये WL के रिस्पेक्ट में है. अब जितना अपन अंदर जाएंगे हर वेट में उतनी ये टर्म अपनी बढ़ती जाएगी. So chain rule of differentiation is, you can see here, for example, you have a function f which is affecting G, which is in turn affecting H, which is in turn affecting I, which is in turn affecting J, which is in turn affecting K. So if you are interested in knowing that how this function K is changing with the respect F, oh no, F ये उल्टा आएगा, sorry. So ये क्या है? ये मेरे पास X इनपुट है जिससे एक नोड बन कनेक्टेड है K से वो जा रहा है J, I is function of J and H is function of I, and then G is function of H, and then F is function of G. ये ऐसा अगर नेटवर्क है और मैं चाह रही हूँ कि how to know that how F is affected by a small change in X. So ये क्या होगा? It is a multiplication of F is a function of G, and so what a small change in G is bringing a change to F. Then it is G is differentiated with respect to H. H is differentiated with respect to I is differentiated with respect to J is differentiated with respect to K is a function of X differentiate. So it will be a product of these terms, which is given. This is chain rule of differentiation. जो भी वेरिएबल के कॉरेस्पॉन्डिंग आपको differentiation निकालना है, you have to recursively apply this chain rule of differentiation. Is this okay? I hope it is okay. So quickly, I like to tell you certain nuances. How do you do weight initialization in the network? So for example, here it is a small network. You have two input nodes. This is the input, one hidden layer, and then one output. So मेरे पास में weights क्या हैं जो initialize करने हैं? W11 dash 12 dash 21 dash, then W11 double dash W21 double dash, and then finally I am producing A21. So weights में हम क्या करते हैं कि usually कई लोग क्या कर देते हैं कि we initialize the weight to 0. So is it a good idea to do a 0 initialization of weights? Anybody? Is it a good idea to do 0 initialization of weight? When I do a 0 initialization, तो आप देखेंगे कि for example आपका activation A11 है. So A11 आपका क्या है? It is W11 dash plus X1 plus W21 dash into X2. Okay? और ये बन गया Z1. Let me write here. A11 equal to sigmoid of this. ठीक है, अगर तो and A, what is A12? This is sigmoid of W12 dash X1 plus W22 dash X2. अगर मेरा W11 dash all weights are 0, तो ये मेरे पास में क्या आ जाएगा? मैं sigmoid की बजाय let's say we take ReLU as activation function. So ReLU लिख लेती हूँ मैं यहाँ पे. So ReLU में you remember ReLU activation function आपको क्या कहता है? It is a max of 0 and X जो input है. तो मेरे पास में यहाँ पे input क्या है? This weight is 0. This is also 0. This is also 0. This is also 0. So A11 will be equal to 0. Similarly, A12 will also be equal to 0. Similarly, if W11 dash is also 0 and this is also 0, तो A21 मेरे पास में क्या हो जाएगा? It is ReLU of W11 double dash into A11 which is 0 plus W21 double dash A12 which is also 0. So this is also equal to 0. So all my activation functions are producing a 0 output, which again when I update using the chain rule, when I do gradient descent, feed forward back propagation, तो weight में update क्या आएगा? 0 का derivative क्या है? 0 आएगा. तो there is no update in the weights. So when you are using ReLU as a activation function and you are doing 0 initialization, your network never learns. When I am doing tan H activation, so tan H is what? If you remember, tan H is e raised to power x minus e raised to power minus x over e raised to power minus x. Now my x, in this case, when I am my all the weights are initialized to 0, I know the activation function में input क्या जाएगा मेरे पास में? E raised to power 0 minus e raised to power minus 0 over. So e raised to power 0 is 1. So numerator 1 minus 1 हो जाएगा, again 0. So it will again produce all outputs as 0. So both in ReLU as well as in tan H, it won't, the network will never learn. तो आप ये एक्सपेरिमेंट भी करके देखना, ऐसा छोटा नेटवर्क बनाना, उसमें रेल्यू एक्टिवेशन फंक्शन लेना, 10H एक्टिवेशन फंक्शन लेना, स्टार्टिंग में आप वेट्स को इनिशियलाइज 0 करना, आफ्टर hundreds or thousands of epochs your weights will never change, they will remain 0. That will show you that the network never learns. So what happens when I have a constant initialization? एंड ये चीज सिग्मॉइड में क्या होगी? सिग्मॉइड में आपके पास में इनपुट जा रहा है, जब ये सिग्मॉइड भी है, सिग्मॉइड में आपके पास में, मैं यहाँ लिख देती हूँ, इनपुट जा रहा है एफ, तो यहाँ पे क्या होगा? 1/1 + e⁻0, तो 0.5 आउटपुट देगा. तो ऑल नोड्स विल प्रोड्यूस द सेम आउटपुट 0.5. सो सेम आउटपुट में जब आप डेरिवेशन भी लोगे तो डेरिवेशन विल आल्सो रिमेन सेम. तो अगेन यू विल हैव द सेम प्रॉब्लम कि आपके पास में द नेट, इट विल एक्ट एज अ लीनियर लेयर बिकॉज एवरी आउटपुट प्रोड्यूस्ड इज सेम. सो सेम आउटपुट है तो डिफरेंशिएशन में वो फिर से 0 हो जाएगा. योर नेटवर्क विल नेवर लर्न. And the same thing happens in constant initialization. If you initialize all the weights to a constant value, then they will generate the same output in the layers. मैं एक में दिखा देती हूँ आपको कि इसको रब कर दूं कि यहीं लिखूं. रब कर देती हूँ, जो अटेंड कर रहे हैं उनको तो समझ आया होगा. So when I am talking of, so this 0 initialization, network never learns. When there is a constant initialization, say it produces same output. All nodes produce same output, which leads to vanishing gradient problem. Because same output है, तो जब आप gradient लोगे तो gradient में activation function same है और उनका differentiation लोगे, it will come out as same. तो आपके पास में again vanishing gradient problem आएगा और वो network will never learn anything. So यहाँ पे आपके पास में convergence problem. जब आपके पास में रैंडम इनिशियलाइजेशन विद स्मॉल वैल्यूज करते हो, तो रैंडम इनिशियलाइज कर रहे हो ऑल द वेट्स एंड द वेट्स आर आल्सो स्मॉल. लेट्स से यू आर कीपिंग इट बिटवीन 0 and 1. तो आप रैंडम इनिशियलाइज करिए वेट्स को, मल्टीप्लाई करिए स्मॉल वैल्यू से सारी वेट्स को 0.0001. तो ये जो आपके पास में वेट्स हैं ये बहुत ही छोटे रहते हैं. तो छोटे वेट में जब अपन ग्रेडियंट भी उनका लेंगे तो स्मॉल चेंज आएगा. तो इट काइंड ऑफ दैट एवरी टाइम द एरर जो लास्ट लेयर में है, जब उसको हम एक स्मॉल वैल्यू से मल्टीप्लाई करके प्रीवियस लेयर में भेज रहे हैं तो वो आपका एरर प्रोपेगेट और भी कम हो रहा है. उसको फिर फर्दर हम स्मॉल वेट से मल्टीप्लाई करके प्रीवियस लेयर में भेज रहे हैं तो वो एरर और भी कम होता जा रहा है. तो व्हेन द एरर इज बैक propagated to the first layer, it remains infinitely small, and which brings a very small change in gradient, which is called a vanishing gradient problem. तो जब random initialization with small values होगा तो vanishing gradient आएगा, which will lead to your convergence problem. And if you are doing random initialization with very large values 0.01 से multiply किया random weights को और initialize करा, आप केरास में या PyTorch में करके देख सकते हैं इसी नेटवर्क को. तो आप जब आप random initialization करिए, फिर सारी values को 0.0, small value means 0.0001 and large value 0.01 is a large value, इससे multiply किया. तो ये जो आपके पास में, लेट्स से आपके पास में हंड्रेड्स ऑफ वेट्स हैं, हम समेशन कर रहे हैं WI इंटू XI, तो ये 0.01 इंटू समथिंग होके इनको आप ऐड कर रहे हो 100 टाइम्स, तो एटलीस्ट आपके पास में वो मैग्नीट्यूड इन टर्म्स ऑफ टेंस तो आ जाएगा. So when you are doing, there is a sigmoid activation function, you are raising it to the power of positive e raised to power something tens, so it will saturate towards 1. And if it is a negative value, which is a large value, it will saturate towards -1. So यहाँ पे again आपके पास में activation function का saturation हो गया, which leads to vanishing gradient problem. प्रॉब्लम। रेल्यू में आपके पास में क्या होगा, वैनिशिंग ग्रेडियंट प्रॉब्लम नहीं आएगी, बट एक्सप्लोडिंग ग्रेडियंट हो जाएंगे, बिकॉज द ग्रेडियंट ऑफ ए रेल्यू फंक्शन इज 1। तो जैसे जैसे मैग्नीट्यूड बढ़ रहा है, ग्रेडियंट भी आपका बढ़ता जा रहा है, एंड देन ग्रेडियंट इज वेरी लार्ज, तो वो बड़ा चेंज लेके आ रहा है, तो then also it leads to a convergence problem, because you are skipping the minimum value, are going from a negative value to a higher value, from a higher value to a negative value. And in TANH also it leads to saturation of the activated output, which leads to vanishing gradient problem. So all the four things are to be avoided with these activation functions. What is preferred is random weights. They are neither too small nor too large for initialization. I hope it made some sense with you people. And now, because we are at the end of the thing, so should I continue with the small to make you understand this chain rule with the help of a functional diagram, or because we haven't taken any break, so you want to end it here? Hello?
Participants can give their answers in chat box.
Continue, please. Okay, so I'll come to the last block that I wanted to tell you. To understand this feed forward and back propagation, there is a diagrammatic help to understand the network, and that is called a functional diagram. What is a functional diagram? As you can see on the screen, every node is represented by an activation function. Let's call it as F. So whatever input is coming into it, so we represent the nodes in the network, we represent with the help of a functional diagram. What is a functional diagram? In a functional diagram, a node is represented with a circle or a square or a rectangle with the function f. It has the input as it has two inputs, x and y. What is the purpose of this node? The node will do, it will feed forward the input and produce the output, which is shown as z here, depending on what is the function. So node मेरा क्या हो गया, एक function, उसमें कुछ input है और ये output produce कर रहा है जो भी function बता रहा है. For example, function is plus, so I'll represent it as a x, y. What it will produce? It will produce x plus y. If the function is a multiplication, and I have again two inputs, let's say it can have n inputs, the output will be x into y. So this is a node. So feed forward step is simple. Take the input, apply the function and produce the output. So every node does this, forwards it to the next connected node, which does the same thing, forwards it to the next connected node and goes to the end. Back, what is back propagation? Back propagation is at the last layer, you will compute the gradient with respect to the last output itself, which will be usually 1. So that is called a upstream gradient from the last layer. It is fed into the node. अब ये node क्या करेगा? Node will compute partial derivatives of the input with respect to its input. It will compute the local gradients. What is a local gradient? Local gradient is partial differentiation of the output with respect to the input. तो मेरे पास कितने इनपुट हैं यहाँ पे? दो इनपुट हैं x और y. आउटपुट क्या था? z था. तो z is differentiated with respect to x, z is differentiated with respect to y. Okay, and this, what this node back propagates is, जो भी upstream gradient आया उसको multiply करा उसके local gradient से और वो output दे दिया. तो यहाँ पे अभी आप डायग्राम में देखिए कि क्या हो रहा है. मेरे पास लोकल ग्रेडियंट क्या है, आउटपुट क्या है, z is differentiated with respect to x, z is differentiated with respect to y. अपस्ट्रीम, अब ये नोड क्या करेगा, ये बैक प्रोपेगेट करेगा अपस्ट्रीम ग्रेडियंट विच इज जो भी लॉस उसके नेक्स्ट नोड का था, डिफरेंशिएटेड विद रिस्पेक्ट टू दिस आउटपुट इनटू इट्स लोकल ग्रेडियंट. तो ये इस इनपुट में क्या बैक प्रोपगेट करेगा dl del L ओवर del Z जो अपस्ट्रीम ग्रेडियंट है इनटू ये लोकल ग्रेडियंट, इसका मल्टीप्लाई किया। यहाँ पे क्या बैक प्रोपगेट करेगा, partial differentiation of L with respect to upstream gradient with respect to Z and the local gradient Z with respect to X। तो ये चेन रूल यहाँ पे अप्लाई होता जाएगा। ये डाउनस्ट्रीम ग्रेडियंट्स हैं। तो फंक्शनल डायग्राम में क्या हो रहा है कि आप जो आपके पास में इनपुट आई उसके ऊपर फंक्शन अप्लाई किया, एक आउटपुट प्रोड्यूस किया। अब जब इसके पास बैक प्रोपगेशन ऑफ एरर आएगा तो जो अपस्ट्रीम ग्रेडियंट आ रहा है वो लोकल ग्रेडियंट से मल्टीप्लाई होके जो इनपुट है उनके ऊपर पास ऑन होगा टुवर्ड्स द प्रीवियस लेयर। दैट इज द जॉब ऑफ दिस फंक्शनल डायग्राम, एज इजी एज दैट। तो चेन रूल कैसे अप्लाई होगा, ऑल अपस्ट्रीम ग्रेडियंट्स मल्टीप्लाइड बाय द लोकल ग्रेडियंट ऑफ द नोड एंड पास्ड ऑन डाउन। तो ये मेरे पास में बहुत सिंपल, हर नोड क्या कर रहा है, अपस्ट्रीम ग्रेडियंट को इससे मल्टीप्लाई किया, इस पे पास कर दिया, इस अपस्ट्रीम ग्रेडियंट को इसके लोकल ग्रेडियंट से मल्टीप्लाई किया, इस पाथ पे दे दिया। अगर इस पे एक और इनपुट होता तो ये अपस्ट्रीम ग्रेडियंट मल्टीप्लाइड बाय द लोकल ग्रेडियंट ऑफ दिस फंक्शन विद रिस्पेक्ट टू दिस इनपुट, और वो यहाँ पे पास ऑन होके वो अपस्ट्रीम ग्रेडियंट बन जाएगा। यहाँ पे कोई नोड होगा उसका अपस्ट्रीम ग्रेडियंट हो जाएगा। सो लेट्स टेक एन एग्जाम्पल। जो अपन ने ग्रेडियंट अपन ने देखा ही है, अपने पास में फंक्शन है, फंक्शन इज माइनस एक्स प्लस थ्री। सो आई विल कॉल माइनस एक्स प्लस थ्री एज क्यू, ओके, एंड एक्स आई कॉल एज माइनस आर आई कॉल एज माइनस एक्स। तो मैंने इसी फंक्शन को लिखा, दिस फंक्शन बिकम्स एफ इज अ फंक्शन ऑफ क्यू स्क्वायर where q is r plus 3 and r is what, minus x। तो मुझे अगर फंक्शन f को डिफरेंशिएट करूंगी तो f is a function of q, तो f is differentiated with respect to q, तो I get 2q। what is q, q is a function of r, तो मैं डिफरेंशिएट करूंगी तो partial differentiation of q with respect to r which is 1, and r is what, it is a function of x, तो I differentiate it with respect to x which is minus 1। तो अगर मुझे निकालना है what is the change in f with respect to x, so it will be a multiplication of how f is changing with respect to q, how q is changing with respect to r, and how r is changing with respect to x। तो ये हमने यहाँ निकाल रखे हैं, ये चेन रूल अपन ने किया था अभी, तो मैं इनको मल्टीप्लाई किया और ये आया अपने पास में। This is an example. So let's do with the help of a functional diagram। तो functional diagram क्या कर रहा है, n input है तो मुझे क्या दे रहा है, function of n output, और ये back propagation of error क्या करेगा, जो भी upstream gradient आ रहा है उसको multiply करेगा function के local gradient से और output दे देगा g into partial differentiation of f with respect to n। So forward is given forward input n, compute fn, backwards is given backward input g, because g is a upstream gradient coming from the next layer to this node, और मुझे output क्या देगा, g into partial differentiation of f with respect to input। So यहाँ पे अपने पास में अभी जो अपन ने करा था वही अपन लेते हैं। Let's say there is a node n and this node has input x। तो ये नोड, ये फंक्शन क्या कर रहा है, ये जो भी वैल्यू आएगी इनपुट उसको माइनस करेगा। तो आउटपुट क्या आया, अगर x इनपुट था तो मेरे पास में फर्स्ट नोड का आउटपुट क्या आएगा, एक मिनट, यहाँ पे x इनपुट आया, माइनस जो भी इनपुट आ रहा है वो माइनस हो जाना चाहिए, तो आउटपुट आया माइनस x। अब इसमें जो भी इनपुट आ रहा है उसमें +3 ऐड हो रहा है तो आउटपुट हो गया -x + 3। जो भी इनपुट है वो स्क्वायर हो रहा है तो आउटपुट फीड फॉरवर्ड स्टेप में इस फंक्शनल डायग्राम में आउटपुट आया -x + 3 का होल स्क्वायर। ओके, सो एट द आउटपुट लेयर व्हेन आई डिफरेंशिएट दिस आउटपुट विद रिस्पेक्ट टू इटसेल्फ, तो मेरे पास में डिफरेंशिएशन हमेशा 1 होगा। तो लास्ट लेयर का फंक्शनल डायग्राम में आपके पास अपस्ट्रीम ग्रेडियंट इज 1 ओनली। अब 1 आया, इस नोड के ऊपर आया, इस नोड में लोकल ग्रेडियंट क्या है, लोकल ग्रेडियंट इज 2n. सो 2n अपने पास में क्या है, n की वैल्यू क्या है -x+3, तो ये 2n मेरे पास में क्या है -2x+6. तो ये आपके पास में ये देखिए, तो ये -2x+6 इंटू 1, ये आपके पास में डाउनस्ट्रीम ग्रेडियंट आएगा यहाँ पे. अब ये इसका अपस्ट्रीम ग्रेडियंट हो गया. यहाँ पे यू आर डिफरेंशिएटिंग n विद रिस्पेक्ट टू x, तो यहाँ पे ये डिफरेंशिएट n विद रिस्पेक्ट टू n, जो इनपुट है x, तो ये डिफरेंशिएशन आपके पास में क्या हो जाएगा, डिफरेंशिएशन आपके पास में 1 हो जाएगा. तो ये 1 से मल्टीप्लाई करेगा n को, तो -2x+6 मल्टीप्लाइड बाई इसका पार्शियल डिफरेंशिएशन 1 आया, तो ये आपके पास में सेम वैल्यू आई, तो यू विल गेट -2x+6. अब यहाँ पे डिफरेंशिएशन लेना है -n का, तो ये डिफरेंशिएशन लोकल डेरिवेटिव क्या आएगा -1. इट इज मल्टीप्लाइड बाय द अपस्ट्रीम ग्रेडियंट, सो फाइनली यू विल गेट दिस एज आउटपुट. सो आई होप दिस डायग्राम इज क्लियर. फीड फॉरवर्ड क्या हुआ, ये कह रहा है कि जो इनपुट आया उसको करिए माइनस इनपुट, तो यू विल गेट x was the input minus, so -x, then whatever is the input +3, so -x+3, then whatever is the input का square, so -x+3 का whole square. What is the downstream gradient? Output layer 1. What is the local gradient? 2 into n. So local gradient क्या हो गया, 2 into n की वैल्यू क्या थी -x+3, तो ये आपके पास आ गया -2x+6. अब ये यहाँ upstream gradient आया. What is the local gradient of n? Local gradient is 1. So this multiplied by 1, you get the same value. This is the upstream gradient. What is the local gradient? -1. So this multiplied by -1 is this. Is this clear? So, और अपन ने देखा है बैक प्रोपगेशन में क्या होता है, जो नेक्स्ट लेयर के एरर आ रहे होते हैं वो एरर क्या है, वो अपस्ट्रीम ग्रेडियंट है. वो आके किससे मल्टीप्लाई होते हैं, लोकल ग्रेडियंट ऑफ द नोड, एंड वो दैट गोज एज अपस्ट्रीम ग्रेडियंट टू द प्रीवियस नोड and to the previous node and to the previous node. So this becomes very easier to understand and represent with the help of the functional diagram. So अब अगर मेरे पास में फॉर एग्जाम्पल यहाँ आ जाइए, किस तरह के गेट हो सकते हैं. I can have a plus gate, adder gate. So what adder gate does is, for forward it will, let's say the input is 3 and 4, it is a plus, so output क्या आएगा मेरे पास में 7 आएगा. तो मेरा ये फंक्शनलिटी क्या है, इफ दिस इज लेट्स से x, दिस इज y, तो x प्लस y यहाँ पे ये ब्लॉक क्या है, नोड इज x प्लस y. सो इफ आई डिफरेंशिएट इट, लेट्स से दिस इज z, ओके. सो इफ आई डिफरेंशिएट इट विद रिस्पेक्ट टू x, दो इनपुट हैं, तो मेरे पास में ये क्या आ जाएगी, इट विल बी 1. and I differentiate it with respect to y, then also it will be 1. So जो भी मुझे downstream gradient आएगा वो it will be equally distributed, it will be same, it will go same, it will be distributed, the same value will be distributed downstream. वो यहाँ पे आपको दिखा रहा है. तो यहाँ देखिए आपको upstream gradient अगर 2 इसमें आएगा तो ये add gate है, तो 2 ही downstream gradient होगा, because local gradient क्या है 1 थे, it is a adder gate. So 1 into जो भी upstream gradient है वो दोनों पे चला गया. अगर मेरे पास में multiply gate है तो z is x into y. तो if I local gradient of z with respect to x will be y, and local gradient of z with respect to x will be equal to so x तो कर लिया with respect to y. This will be x. तो आपके पास में देखिए जब ग्रेडियंट आएगा मल्टीप्लाई में अपस्ट्रीम तो आपको दिक्कत ही नहीं है, 2 इनपुट 3 इनपुट मल्टीप्लाई यू गेट अ 6 आउटपुट. डाउनस्ट्रीम ग्रेडियंट अगर मेरे पास 5 है तो इधर ये x पे जाने पे दिस ग्रेडियंट विल बी मल्टीप्लाइड बाय द y, द अदर वैल्यू. देखिए डिफरेंशिएशन ऑफ z विद रिस्पेक्ट टू x क्या है y. तो यहाँ पे ये जो डाउनस्ट्रीम ग्रेडियंट है 5 विल बी मल्टीप्लाइड बाय 3 एंड यू गेट अ 5, यहाँ पे 15. एंड यहाँ पे क्या आएगा 5 will be multiplied by 2 and you will get a 10. So in a multiplication The values are swapped, the input values are swapped and they are multiplied by the upstream gradient as local gradients and ये distribute हो जाती हैं. अगर अपने पास में कॉपी गेट है तो कॉपी गेट में तो वो सेम ही ग्रेडियंट कॉपी हो जाता है. तो 7 वैल्यू थी, ये आपके पास डिस्ट्रीब्यूट होके 7 आ गई. अगर इसके पास में मेरा ग्रेडियंट यहाँ से 4 आ रहा है, लेट्स से यहाँ पे 2 आ रहा है, तो ये दोनों ऐड होके यहाँ पे बैक स्ट्रीम में कॉपी हो जाएंगी. सिमिलरली देयर इज अ मैक्स गेट, तो मैक्स गेट में जो भी मैक्सिमम वैल्यू है वो आउटपुट जा रही है. अब ग्रेडियंट आया तो ग्रेडियंट तो उसी पे फ्लो करेगा जिससे इनपुट आया था, तो द सेम ग्रेडियंट विल गो टू द मैक्स वाला इनपुट, नॉट टू द other values. So this is how gradients are distributed back in functional diagrams. So आप एक और एग्जांपल अपना यहाँ छोटा सा मैंने दिखा रखा है. f is a function of 3 values x, y and z. So मैं इसको functional diagram में I make 2 nodes, x plus y as one node and this is multiplied by z as another node. So मेरे पास में जो भी input आ रहा है मैं उनको add कर रही हूँ. For example, input is 1 and 4, I get output which is 5 and this is z is a value which is 10 and this is another node which is x plus y into z, so n into m, so output is 50. So now in this case when you are doing back propagation of error, तो आप मुझे बताइए यहाँ पे तो सबसे पहले क्या आएगा, upstream gradient will be 1. ओके अब इसमें मेरे पास दो इनपुट हैं, एक इनपुट n और एक m. So when I differentiate this, let's call it as z. So when I differentiate z with respect to n, I get m. When I differentiate it with respect to m, I get n. So ये upstream gradient will be multiplied by, यहाँ पे तो m से multiply होगा, तो यहाँ पे ये 10 से multiply होके यहाँ पे 10 जाएगा और ये इधर जो जाएगा वो 5 जाएगा. तो ये अपन यहाँ पे देख लेते हैं, आप ये देखिए ये है 1, ये यहाँ पे 5 डिस्ट्रीब्यूट हुआ, यहाँ पे 10. तो मल्टीप्लीकेशन था तो ये चेंज हो गया, तो n इंटू एम, तो जहाँ n वाला इनपुट है वहां तो m से मल्टीप्लाई होगा, जहाँ m वाला इनपुट है वहां n से मल्टीप्लाई होगा. And then there is another example. This is another example. So how do you proceed? You proceed by, there is you want to solve this function. So here I am breaking it into every individual block. So मेरे पास e की input क्या आ रही है, w naught x naught. So यहाँ पे w naught x naught एक multiplier gate बना दिया, w1 x1 another multiplier gate. इसमें add करना है w2, तो adder gate जिसमें ये तीनों, ये इधर जाना चाहिए, ये टाइपो हो गया. So पहले ये w naught x1 plus w1 x1 मल्टीप्लाई होके यहाँ ऐड हो रहे हैं, फिर इसके अंदर ऐड हो रहा है w2. अब इसके अंदर मैं फिर से क्या कर रही हूँ, इसका नेगेटिव कर रही हूँ, आई मल्टीप्लाई इट बाई -1. फिर ये क्या करना है, e रेस टू पावर करना है, तो e रेस टू पावर फंक्शन है. फिर इसमें ऐड क्या करना है, e रेस टू पावर +1 करना है, तो जो भी इनपुट है उसमें +1. फिर ये 1 ओवर ये है, तो दिस इज द फंक्शनल डायग्राम. ओके एंड इसका आपको यहाँ पे दी हुई है कि अगर कोई इनपुट वैल्यू ऐसी हुई तो आउटपुट क्या आएगी. यहाँ पे मैंने आउटपुट कंप्यूट करा हुआ है. दिस इज अ एक्सरसाइज फॉर यू टू कंप्यूट द डाउनस्ट्रीम ग्रेडियंट्स. तो ज्यादातर ग्रेडियंट्स लोकल आपको पता है, मैं बता देती हूँ. व्हेन यू डू ग्रेडियंट ऑफ ई क्या होता है, सॉरी, gradient of ax there is a function 1 over x, so f equal to, so partial differentiation of equal to I think ये, so इससे इसके ये तो 1/n है, इसका ये हो गया e raised to power x है, e में कुछ मल्टीप्लाई हो रहा है तो उससे मल्टीप्लाई होगा, रेस्ट ऑफ द ग्रेडियंट्स वी ऑलरेडी नो, एडिशन एंड मल्टीप्लिकेशन। तो इसको यूज करके यू प्लीज कंप्यूट द डाउनस्ट्रीम ग्रेडियंट फॉर दिस फंक्शनल ग्राफ, एंड फिर आप देखोगे कि इसको इतना कॉम्प्लिकेट करने की भी जरूरत नहीं है। ये जो हो रहा है this I can change to simple sigmoid function। और क्यों इसको करूंगी, बिकॉज डेरिवेटिव ऑफ a sigmoid is f dash x will be plus e raised to power minus x का -1, so इसका जब डेरिवेटिव लेंगे तो वो आएगा -1 into 1 plus e raised to power -2 into e raised to power minus x into -1, so which will be equal to e raised to power minus x 1 plus e raised to power minus x whole square. So when I do which is kind of 1 minus fx into fx. So derivative of a sigmoid actually क्या होता है, वो होता है sigmoid into 1 minus sigmoid। इसलिए ये फंक्शनल ब्लॉक को हम ऐसा कर देते हैं, बिकॉज सेम वैल्यू को 1 माइनस उस वैल्यू से मल्टीप्लाई करना है। तो इतना डिटेल you can draw the functional diagram to the minimum, bring it down to the minimum elements that are getting operated, or you can use a complex block also, because the block can have simple derivatives. So it depends what kind of detail you want to include in the functional diagram. So that's all for today. Any questions? Hello.
If someone is having any query, they can write it up in chat box.
I hope you understood something about this deep neural networks, how to do the parameter initialization, how to understand it with the help of a, in case you want to connect for future guidance, you please mail me. My mail ID is nn.csc@mnit.ac.in. Is this okay? So okay. So I'll share the slides with your coordinator, and then they will mail the slides to you people. You can always send a mail if you have any query or any difficulty. I'll try to answer all the queries. Thank you very much. I hope I was, because I cannot see you guys, I cannot hear you guys, so it has become it. I don't know what level you have understood, but I hope something has been made easy for you in understanding these deep neural networks. So every network which has n number of layers more than 2 is called a deep neural network. How many layers you can have, as many as you want, how many nodes you want, as many as you want, but as you increase the number of layers, as you increase the number of nodes, the number of parameters increases. And this is the fully connected block in all the other deep learning or architecture that you have learned, कि आप कन्वोल्यूशन अप्लाई करके एक फीचर वेक्टर फ्लैटन लेयर लेके आते हो और उसको फिर बोलते हो फुल्ली कनेक्टेड लेयर। तो वो फुल्ली कनेक्टेड लेयर में लर्निंग कैसे होती है वो अपन ने कवर किया है। This is the state of art. Artificial neuron was designed in 43. When the Turing test was defined in 50s, can machine thinks? Yes, they can. The birth of AI happened with thinking machines. Perceptron, the first single layer perceptron was defined in 57. Then there was a dark age because of this non-linearity problem, ki this perceptron cannot solve non-linear problems. But with the coming up of multi-layer perceptrons and this back propagation algorithm, there was a second golden age in these neural networks. And then suddenly SVMs becomes important because the compute capability was very small. So learning deep neural network was difficult. So SVM gained popularity, but in the late 2000s, early 2000s, AlexNet and all, they came up with the idea of this John, how do you spell? I don't know. They came up with AlexNet, and this was the first CNN architecture, which brought down the error rate in recognition by 20% or 23% in the very large scale object recognition competitions, which were happening every year. And this brought the third golden age in this neural network. And now we have so many architectures. We have generative adversarial networks, which came in 2014, transformers in 2017, then GPT, chat GPT, and now we are at generative AI. We are generating text. We are not even interested in thinking machines. We are saying that we should have creative machines. What we want to create art, we want to create text, we want to create things which are already not there. So we want artistic in guidance by the machine itself, which leads to generative AI. So presently we are at generative AI. Okay, so thank you very much. Unless there is any other question, I exit now.
So, ma'am, I think there are no more queries.
Okay.
So, on behalf of organizing team, a heartful thank to you, ma'am, for today's enlightening session on deep learning, covering topics like back propagation, activation functions, and weight initializations. We truly appreciate the effort and depth you brought to the topic. Thank you once again, ma'am, for your time.
Okay, thank you very much.
To the participants, we will meet again at 1:50.